The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope all are doing good with your improvement exam. You must be busy getting up early, preparing for your exams. Continue this even after the exams are over. Try to get up early, be active, because once you have finished this improvement, within 2 months we are going to appear for our board exam, right, which is very essential for us. Definitely we'll be doing well, but of course early to bed, early to rise is very important. So stop working late night, getting up late in the morning. All those things will affect our both body and mind. So I want you all to be healthy children, take good diet, proper diet at proper time interval, and this will all happen only when you get up early in the morning. Okay. So we were seeing about valence bond theory. So now we'll just focus into crystal field theory, which is again focusing on the bond formation between the metal atom and the ligand. When you say crystal field theory, there were some failures with valence bond theory. That is, they were not able to explain why with the coordination number 4 a complex is showing both tetrahedral and square planar, and it was not focusing on the color of the complex, right. So in this crystal field theory, we are going to learn about how the metal atom and the ligands are bonded with each other, on what basis the bonding formation takes place. So now let us learn why this crystal field theory was invented and how this theory is being implemented in the coordination compounds. What is crystal field theory? There is an electrostatic interaction between the metal ion and the ligand. My metal ion and the ligand is being bonded to each other is just because of the electrostatic interaction. What is electrostatic interaction? We know the opposite charges, they attract each other. So metal atom being positive in charge will attract a negative charge. So we know ligands can be negative or even neutral. So the attraction between the metal atom and my ligand. So if I am going to take a complex, this is my octahedral complex where M is my central metal atom and I have my ligands surrounded by it. I have 4 bromine atoms which are my negative ligands and 2 water molecules which are my neutral ligands. Now if I say a negative ligand is bonded to my metal atom, that such type of interaction we call it as an ion-ion interaction. So that interaction is called as ion-ion interaction. The same way, if the water molecule being a neutral ligand is bonded with a metal atom, I call it as a ion dipole interaction. So interaction is the same, both the ligands, that is it can be a neutral ligand or my negative ligand, it is bonded with my central metal atom, but the nature of the interaction is different. Here it is ion-ion and the other one is ion dipole, because we know the neutral molecules, they are dipolar in nature. So what happens here? After this electrostatic interaction, the metal atom being a transition element possesses a d orbital. So we know there are 5 d orbitals in the d subshell. So they are dxy, dyz, dzx, dx square minus y square and dz square. I am posting a video for you for better understanding using graphic method so that you can understand how these orbitals lie in different axes, because as you learn in mathematics 3 coordinates x, y, z, you will come to know how these orbitals are lying in different axes. Now in this case dxy, dyz, dzx are away from the ligand, so they have a lower energy, that is the repulsion is less. But when you take dx square minus y square and dz square, they are towards the axis, so they have more energy and more repulsion towards the ligand. Repulsion is between the electrons when it is bonded to the central metal atom, because we know this is my d subshell and I have electrons in the d subshell, and electrons being negatively charged, they can repel each other, because as we have learned, like charges repel, unlike charges attract. So what happens here, these like charges they can repel each other, but these d orbitals they have degeneracy. Now what is degeneracy? Degenerate means possessing same energy level. So these 5 orbitals they possess same energy level, and so what happens, there can be a repulsion. So repulsion will be more if the metal atom is directed towards the ligand. The metal atom is directed towards the ligand, the repulsion will be more. When it is away from the ligand, the repulsion is less. Now because of such repulsion happening between the electrons in a complex, the degeneracy becomes no more, that is it is removed, it becomes nil. And because of that, what happens, that particular d subshell starts getting splitted, because when all the 5 were degenerate having same energy, they were happy. But once there was a small difference in their energy level, they couldn't stay together. So what happened? They planned to get split into 2 different categories, one with a lower energy and one with a higher energy. So which we will be seeing now how the splitting of the d orbitals takes place. What is crystal field splitting? So if you see here, splitting of the degenerate levels. What is the degenerate levels? The 5 orbitals of the d subshells are in one particular level, that is they are having same energy. Such an energy level we call it as degenerate levels. Splitting of the degenerate levels due to presence of ligands. So ligands are wholly responsible for the crystal field splitting. So the ligands, depending on the ligands, the crystal field splitting takes place. Now that is with respect to a definite geometry, that is it can be tetrahedral, it can be octahedral. Now how does it work? Let us see. So this is my energy level, these are my metal d orbitals, all are in the same energy level, but when slowly they get reach into the average energy level, but after getting the average energy level, the ligand starts approaching the central metal atom. Once the ligand starts approaching, the degeneracy is lost, which means they are not possessing the same energy level. They become different in their energy level. So what happens there? The splitting takes place. We have dx square minus y square and dz square getting into the Eg level, that is the higher energy level, and we have dxy, xz and yz getting into the T2G level, which is the lower energy level. The difference between these two is represented by del O, which is called as energy separation. Now what happens in this case? This 2, that is the 2 Eg. 2 Eg means this is 1 Eg, this is second Eg. The 2 Eg orbitals will be increased by 3 by 5 del O, and the 3 T2G orbitals will be decreased by 2 by 5 del O. That is the energy difference. This much is the energy difference they are getting increased, and this is the energy difference that they get decreased. Now this splitting depends upon the field, that is the strength of the ligand. So the strength can be strong ligand, it can be a weak ligand. If it's a strong ligand, there is a large splitting taking place, and if it's a it's a weak ligand, the splitting will be very, very small. Such a series where the arrangement of ligands into various levels, we call them as spectrochemical series. So you can see in your textbook with I minus, Br minus, where carbonyl is having the strongest field and the weak are the negative ligands like iodide, bromide and all comes at the end. Strongest is carbonyl, then comes cyanide, then ethylene diamine, ammonia, then comes EDTA, all those things, isocyanide, water, oxalato, all those you are having. So please study the basic ligands at least that we will be getting. Now we will learn about how the weak ligands and strong ligands influence the crystal field. Okay, now we shall see how the fourth electron after the degeneracy is being removed, how the splitting has taken place, and now how the fourth electron will be doing a pairing by either whether it will get into the T2G level or it will jump into my EG level. See, for the D4 combination, that is I have my subshell like this 1, 2, 3. Now the fourth electron should enter. Now where will it go? The fourth electron can either pair up with the T2G level or it can go into the EG level. How does this takes place? If my energy separation is less than my pairing energy, then that type of ligand we call them as weak ligands. Those ligands for which the energy separation is less than the pairing energy, they are called as weak ligands and they form a high spin complex, which means the fourth electron will jump into the EG level. How is this placed, children? We have like this dxy and then here at the EG level. So 1, 2, 3. Now the fourth electron, instead of going here, for the weak ligands it will be going on the top. It will not do the pairing. But for ligands which are strong ligands, where the energy separation is greater than the pairing energy, the fourth electron will join up with the T2G level. So here the configuration is T2G3 EG1, one electron present in EG level. Here it is T2G4 EG0, that is the fourth electron is entering the T2G level. You have the explanation given for even tetrahedral complex, it forms the same type. Instead of, we know octahedral geometry, for tetrahedral geometry what type of hybridization takes place. But instead of del O, that is octahedral, we use del T, that is tetrahedral, del tetrahedral, that is energy separation for tetrahedral complex. Now color of the coordination compounds is mainly due to the presence of the ligands that are present, that gets bonded with a central metal atom. That is 100% responsible by the complementary, the color that has been absorbed. That is, if the color generated from the wavelength that is left over is one color, the complementary color will be the color that is appearing in the complex. See, you have a table given to you where the color that is being absorbed and the color that is seen in the complex is being given. Just go through it because it can come in 1 mark question. And the presence of the ligand will make the complex colored one. Like if you have copper sulfate pentahydrate, when 5 water molecules are present, it's a blue crystal solution. But when water ligand is being removed, it becomes a colorless complex. And you have been given an explanation in page number 253, children, here, where you have nickel with 6 water molecules. When 1,2 ethane 1,2 diamine is added, when 1 molecule is added, it becomes pale blue. When 2 molecules of ligand is added, it becomes blue purple. When 3 molecules of the complex is being added, it becomes violet. Right. So when you are adding another ligand, you remove the water molecule slowly, the color of the complex actually changes. So that shows that presence of the ligand or nature of ligand is also responsible for the color of the complex. Limitations of crystal field theory mainly does not focus on the covalent character, and it also not says that the negative ligand should be having a strong power towards the metal atom. But if you see the spectrochemical series, the negative ligands are made as the weak ligands are being placed at the left extreme, that is at the end of the spectrochemical series with a lower energy level. So some of the assumptions for this crystal field theory has not even been clarified by this theory. So with this, the crystal field theory is getting stopped. Now we will be learning about bonding in metal carbonyls and some stability of the compounds. I have come to the last part of this lesson, bonding in metal carbonyls. Bonding we have learned now, valence bond theory, crystal field theory, but apart from that, carbonyl compounds, when I say CO is a ligand, we know which is the strongest ligand of all the ligands. So that CO ligand, when it bonds with the metal ion, it forms two type of bond. One is a sigma bond where the free electron from the carbon, it's been donated to the metal ion, and it also forms two pi bonds where the ions from the metal atom actually gets bonded with the filled, that is the electrons from the filled d orbitals get bonded with the carbon of the p orbital. So there are two pi bonds and one sigma bond which is formed by the metal carbonyl bonds. We have different structures with square planar, trigonal, bipyramidal, octahedral. So many metal carbonyls are present. Now how to find the stability? When the metal reacts with the carbonyl compound, that is when the ligand, it forms a compound. Now this reaction shows that it is reversible and it forms a complex and it can also dissociate. It's a step process where metal combines with one ligand forms Ml, combines with the second ligand forms Ml2, Ml3, Ml4, where K1 and K2 being the stability constant, stepwise stability constants. So at that time what happens, we used to find out the stability, that is dissociation constant, by writing the concentration terms of the product by the reactants. So that overall constant beta 4 will be for the fourth step, which is a combination of all K1, K2, K3 and K4. So what happens, there is a formation constant and there is a dissociation constant also. So more is the stability, more is the ability of the compound to get proportioned into the solution form. Because we know they exist as ions and they are surrounded by the ligand molecules, but when the solvent particle comes and interact with the metal atom, they can get distracted. So that depends on the stability constant value. That has been given an example to you in the textbook. And then you have importance of coordination compounds, around 8 to 10 points are given. Please go through all the importance of coordination compounds, because you have Wilkinson catalyst, some of the important points where it can come in 1 mark question. So with this, the chapter coordination compounds is getting over. We will be starting with organic chemistry from the next class, where I will be showing the whole lesson through the PDF, where you can easily follow, because every reaction is important. I will be using the pointer to note down the important points for you, or a highlighter, so that you can also mark it along with that in your textbook. So keep your textbook ready when you are getting into your organic classes. So if you have any doubt, kindly contact me, children. All the best for your improvement exam. Do well and do take care. Bye.
Crystal field theory. In general, a coordination compound is formed when the vacant d orbitals of the central metal atom overlap with the filled orbitals of the ligands. The magnetic nature and geometry of such coordination compounds is explained by the valence bond theory. But the valence bond theory has some limitations. It does not Explain if the geometry of a metal surrounded by 4 ligands is square planar or tetrahedral. Predict the color exhibited by the coordination compound. Distinguish between weak and strong ligands. To explain the color exhibited by the coordination compounds, a new theory called the crystal field theory was proposed by physicists Hans Bethe and John Hasbrouck van Vleck. Let's understand the crystal field theory in detail. The crystal field theory states that complex compounds are formed due to the electrostatic interaction between the central metal ions and ligands that act as point charges. If this interaction takes place between negative ligands and metal ions, then it is called ion-ion interaction. And if the interaction takes place between neutral ligands and metal ions, it is called ion-dipole interaction. For example, in the triamine trichlorido-cobalt-3 complex ion, the negatively charged chlorine ions and the cobalt metal are held by ion-ion interactions. However, the interaction between the neutral ammonia ligands and the cobalt metal is said to be an ion-dipole interaction. Let's now take the example of the potassium hydrocyanoferrate 3 complex to understand the crystal field theory. In this complex compound, the central metal is iron, which has an atomic number of 26. The electronic configuration of iron is 4s2 3d6. In the complex potassium hexacyanoferrate 3, iron exhibits +3 oxidation state. Hence, the electronic configuration of iron-ion becomes 4s03d5. Observe that the d orbital of iron is half filled and hence it has a stable electronic configuration. These 5d orbitals of the iron-ion possess equal energy. Such orbitals are called degenerate orbitals. However, when the ligand approaches the central metal ion, there is repulsion between the orbital electrons of the metal ion and the electrons of the ligands. As a result, the d orbitals split, thereby forming orbitals of different energies. Let us understand how crystal field splitting occurs in an octahedral complex. According to the crystal field theory, an octahedral complex is formed because of the electrostatic interaction of the central metal ion with 6 ligands. In the octahedral complex, the metal ion is at the center of the octahedron and the 6 ligands lie at the 6 corners of the x, y and z axes. The orbitals of the metal ion which lie along the axes experience more repulsion from the ligands compared to orbitals lying between the axes. Observe that the dx2y2 and dz2 orbitals lie along the x, y and z axes. Hence, these 2 orbitals repel the electrons of the ligands, thereby resulting in an increase in their energy levels. Hence, the orbitals which lie on the axes dx2y2 and dz2 possess higher energies than the dxy, dyz and dzx orbitals which lie between the axes. This results in splitting of the degenerate d orbitals into 2 sets of different energies. This splitting of the d orbitals is termed as crystal field splitting in octahedral complexes. The orbitals dxy, dyz and dzx occupy the lower energy level, as they experience a less repulsive force from the ligands. The orbitals dx2y2 and dz2 occupy the higher energy level. The lower energy level is named as T2g, whereas the higher energy level is termed as Eg. The energy separation between the two energy levels is denoted by delta O. Let us understand how crystal field splitting occurs in a tetrahedral complex. Tetrahedral complexes are the second most common type of complexes. Here, 4 ligands form a tetrahedron around a metal ion. The copper ion in the tetramine copper-2 sulfate complex is surrounded by 4 ammonia molecules which act as ligands, thereby resulting in a tetrahedral shape. Let's look at the crystal field splitting in this tetrahedral compound. Unlike in the case of the octahedral complex, in a tetrahedral complex, the dx2y2 and dz2 orbitals of the metal ion lie between the x, y and z axes, and the dxy, dyz and dzx orbitals of the metal ion lie along the x, y and z axes. The orbitals of the metal ion which lie along the axes experience more repulsion from the ligands as compared to that experienced by the orbitals lying between the axes. Hence, in a tetrahedral complex, the dxy, dyz and dzx orbitals which lie along the axes experience more repulsion from the ligands when compared to that experienced by the dx2y2 and dz2 orbitals which lie between the axes. The orbitals experiencing greater repulsion tend to attain a higher energy level. Therefore, the orbitals which lie along the axes, the dxy, dyz and dzx orbitals attain higher energy than the dx2y2 and dz2 orbitals which lie between the axes. This results in splitting of the degenerate d orbitals into 2 sets of different energies. This splitting of the d orbitals is called crystal field splitting in tetrahedral complexes. The orbitals dx2y2 and dz2 occupy the lower energy levels as they experience a relatively less repulsive force from the ligands. The orbitals dxy, dyz and dzx occupy the higher energy level as they experience a more repulsive force from the ligands. The lower energy level is named as Eg, whereas the upper energy level is termed as T2g. The energy separation between the two energy levels is denoted by delta T. Let's quickly recapitulate the phenomena of crystal field splitting in octahedral and tetrahedral complexes.